Imagine like an automated assembly line moving a massive 2-ton car chassis at lightning speed,
Hmm.
and it snaps to a halt, needing to be accurate to, I mean, literally a fraction of a millimeter to get its next weld. Today, we're doing a deep dive into the hidden mechanical language that makes that impossible precision a reality.
It really is its own language.
Yeah. We are translating all this dense engineering vocabulary into the high-level insights you need for your next manufacturing R&D discussion.
And, that millimeter precision really starts with how you connect the internal components.
Right.
Because if a gearbox is attached to a drive pulley using a traditional keyway, which is just a single notch and a key.
Oh, yeah, the classic setup.
Exactly.
Yeah.
But the massive repeated torque is eventually going to just batter that notch out of shape.
And then you get that mechanical slop.
Right, which we call backlash.
Yeah.
So to eliminate that completely, high-end systems use a shrink disc instead.
Okay, so rather than relying on a tiny notch to handle the load, it's a keyless connection using pure compressive friction.
Yes, exactly.
I always think of it like it's essentially like wrapping a heavy-duty steel collar around the shaft and driving wedges into it, like a Chinese finger trap.
That's a great analogy. The tighter you bolt the wedges, the more brutal the compression becomes. It locks the components together with absolutely zero backlash.
Wow.
That compressive force ensures the connection never slips. But locking the gearbox to the shaft is really only half the problem.
Wait, really? What's the other half?
Well, if the connection holds perfectly, but the shaft itself twists like a wet noodle under that immense torque.
Oh, right. You still lose your exact positioning.
Precisely. That's why our next critical term is torsional stiffness.
Torsional stiffness. So resisting twisting forces.
Right. It's a system's ability to resist elastic deformation. High torsional stiffness is what allows those huge indexing tables to stop moving rapidly without vibrating.
Which cuts down on what engineers call settling time.
Exactly. It drastically reduces settling time.
Wait, but if you're trying to stop a massive steel shaft from twisting under like thousands of newton meters of force, wouldn't the easiest solution just be to make the shaft completely solid, just make it way thicker?
I mean, it seems logical, but adding raw mass actually makes the problem worse.
Really?
How so?
Because a heavier solid part increases inertia. That means the motors have to work even harder to stop it.
Oh, of course.
So instead, engineers use clever geometry. They increase the outer diameter of the shaft, but they make it hollow.
Ah, okay.
This concentrates the material exactly where the twisting stresses are highest, right on the outer edge, which maximizes stiffness while keeping the total weight low.
That is so smart. So, okay, you've engineered this perfectly stiff, tightly gripped, low inertia system, but then you deploy it into this chaotic, real-world factory environment where loads fluctuate wildly. How do you account for, say, a conveyor belt that suddenly jams?
Yeah. Or one that constantly stops and starts. That's where you apply a service factor.
A service factor. Right. It's an empirical multiplier engineers use to over-engineer the torque rating based on the specific application and, the daily runtime.
So if that conveyor system gets hammered by constant shock loads from starting and stopping, you don't just design for the average running torque.
Not at all. You might apply a service factor of 1.5, meaning you rate the gearbox to handle 50% more than the calculated baseline.
Just to prevent premature fatigue failure.
Exactly.
It's like buying a winter coat. You don't buy one just for mildly cold weather. You buy it for a blizzard. You're building in a permanent buffer.
That's a perfect way to put it.
Yeah.
But there is a systemic trade-off when you intentionally oversize your transmission components like that.
Is there? What's the catch?
It hits right at the system's efficiency under partial load.
Oh, I see.
Because inside any gearbox, you have constant mechanical drag. Things like oil seals, bearing friction. That internal friction doesn't just magically scale down because the machine is doing a lighter job.
Right. The seals are still rubbing just as hard.
Exactly. So if your oversized reducer operates well below its rated capacity, its overall efficiency percentage just plummets.
Wow. So the robot practically pays a higher, friction tax when it's just idling or doing light work?
Precisely. Which makes predicting the actual energy consumption of a large automated facility surprisingly complex.
I can imagine.
It's a huge variable, and since that baseline friction is a constant physical reality, you have to manage the resulting heat and wear before it tears the system apart.
Right. You need to keep it alive.
Yeah, and for horizontal gearboxes, the solution is remarkably low-tech. It's Splash lubrication.
Wait, splash lubrication, you mean literally just splashing oil around?
Literally.
Mm.
The rotation of the gears just sloshes oil from a reservoir at the bottom of the casing onto the surrounding gears and bearings.
That is so ironic.
How so?
Well, you have this incredibly advanced facility driven by millions of lines of code, precision sensors, lasers, and the ultimate fail-safe keeping the hardware alive is just gears splashing in a puddle.
I know, right?
Yeah.
But sometimes the simplest physics are the most reliable. As long as you maintain the exact specified oil level, there are no complex pumps to fail.
And no external cooling hoses to leak.
Exactly. Just mechanical rotation doing the work.
It's such a great reminder of the physical constraints in automated design. I mean, we zoomed all the way into the compressive friction of a shrink disk, looked at the hollow geometry of torsional stiffness, calculated surface factors for shock loads, and ended up managing the inevitable friction tax with, well, splashing oil.
Understanding these core concepts really gives you a much clearer picture of why certain R&D decisions get made on the factory floor.
It really does. But, it makes you wonder.
What's that?
Well, if machines are inherently inefficient at partial loads purely because of that constant physical friction, how might future engineers solve this?
That's the million-dollar question.
Right. If the mechanical language keeps evolving, will something like magnetic levitation eventually eliminate physical contact inside transmissions entirely? Maybe one day, managing oil levels and that friction tax will be a problem we only read about in history books. Just something for you to chew on until next time.